The Constitution of India, Preamble. We, the people of India, having solemnly resolved to constitute India into a sovereign, socialist, secular, democratic republic and to secure to all its citizens justice, social, economic and political, liberty of thought, expression, belief, faith and worship, equality of status and of opportunity, and to promote among them all fraternity, assuring the dignity of the individual and the unity and integrity of the nation. In our Constituent Assembly, this 26th day of November 1949, do hereby adopt, enact and give to ourselves this Constitution.
Let us now learn about some of the properties, or I would say rather the reactions of haloalkanes. Nucleophilic substitution reaction, elimination reaction and reaction with metals. If you see children, these haloalkanes, they undergo nucleophilic substitution reactions. You have already learnt in +1 that nucleophiles are electron rich species, so they will attack where the substrate molecule is electron deficient. They have lot many electrons with them, so they are looking for centers where there are no electrons. So they go and get themselves attached to that particular position. The reaction in which nucleophile replaces already existing nucleophile in a molecule is called as nucleophilic substitution. So there is already a nucleophile, this goes and replaces that particular nucleophile. You call that reaction as a nucleophilic substitution reactions. A nucleophile reacts with haloalkane. This is my nucleophile which is electron rich. This is my haloalkane. I have carbon. Now these three are the bonds. It can be hydrogen or it can be methyl group, anything. I have my halogen which is X. So we know it has got delta plus and delta minus. Now children listen. This nucleophile will attack the haloalkane which has got a partial positive charge. This is a nucleophile which is electron rich species. Being negatively charged, it will look for a positive center. So this comes and attacks my carbon. So when this comes and attacks the carbon bond, a substitution reaction takes place and halogen atom called leaving group departs as a halide ion. So when this nucleophile comes and attacks my carbon, this negative charge no more remains there. It comes out as a leaving group, which we call it as a halide ion. So it is called as nucleophilic substitution reaction. Why? Because this reaction is being initiated by the nucleophile. It is one of the most important reaction. From this nucleophilic substitution, we will be learning about two important types of reaction. One is nucleophilic substitution 1 and SN2, that is substitution nucleophilic bimolecular. So when I say unimolecular, bimolecular, we have already learnt in chemical kinetics about molecularity. If the rate of reaction depends on one reactant, you call it as unimolecular. When it depends on two reactants, you call it as bimolecular. So here we are going to study about substitution, unimolecular and bimolecular. Before getting into unimolecular and bimolecular, you should also learn about ambident nucleophiles. Now what are ambident nucleophiles? Groups like cyanides, nitrides, they possess two nucleophilic center. Means they can attack the carbon through two centers. Such nucleophiles you call it as ambident nucleophiles. So the cyanide group, when I say CN, can attack through the carbon center or can attack through the nitrogen center. So you call it as cyanide and isocyanide. So that is again a ambident nucleophile. Similarly, you have nitrides also where oxygen can attack and also nitrogen can attack. NO is also there, ONO is also there. So now we will get into the most important part of the properties, which is substitution nucleophilic bimolecular. I want you all to understand, listen very carefully, children. First one is substitution nucleophilic bimolecular, which is SN2. The reaction between alkyl halide, that is CH3Cl, and hydroxide ion, which is OH minus, yield to methanol and chloride ion. It follows second order kinetics. In chemical kinetics, we have learnt if the order is 2 or the molecularity is 2, it depends on both the reactants. So, the rate depends upon the concentration of both the reactants. So, what is my first species here? It is CH3Cl, which is my alkyl halide. What is this? This is my hydroxide ion. So, now when this nucleophile is going to attack my carbon center from here, I get an intermediate state formed, what is called as a transition state. Now, listen very carefully what is happening here. I have my carbon. Now, these three hydrogens lie like this, one on the top and two on the bottom. I have this OH minus coming attacking my carbon, which is again forming a temporary bond. The bond which is going to be formed now, which is not completed, and the CCl bond, which is also expressed in dot lines, which means this is about to break. The COH bond is about to get formed and the CCl bond is about to get break. So, what happens here? Now, this is my most important transition state where one carbon is bonded to 5 different groups, 5 different atoms. So, you know this is not stable and this is called as a transition state. The COH bond is about to get formed, the CCl bond is about to get broken, right? It's going to get dissociated. So, what happens after this transition state? OH is already attacked the carbon from the back side, because from the front side the Cl is already placed here. So, the back side attack is there. So, the CCl bond gets break and you get a Cl minus ion, that is my chloride ion formed. So, this is my structure which is formed as a product. If you see the reactant and the product, here my group Cl is on the right side, but here the group OH is on my left side, which means the configuration or the structure is being inverted, right? There is an inversion in the configuration. So, the above reaction can be represented like this. So, you get a green ball on the right here. After this is getting attacked, what happens? The green ball breaks and this comes and attacks on the left side, that is back side of the molecule or the structure. So, what happens here? The incoming nucleophile, now listen carefully, this is more important. The incoming nucleophile interacts with the alkyl halide, causing the carbon halide bond to break. The carbon halogen bond actually breaks and a new bond is formed between the carbon and the attacking nucleophile, which is my OH minus. So, CO bond is formed between carbon and OH. Since the two process takes place simultaneously in the single step, so there is intermediate formed will immediately break into the products. Okay. Now, the 3 carbon hydrogen bonds of the substrate start moving away from the attacking nucleophile. So, the transition state, all the 3 CH bonds are in the same plane. And what happens? The attacking and the leaving nucleophiles are partially attached. The bond is not so stronger. COH bond is about to get formed, CBr bond is about to get broken. So, there is an inversion in the configuration. So, this we call it as SN2 mechanism. This is the original structure, but this is a mirror image. This is actually formed. You get the opposite side attacked. Okay, children. Since this reaction requires approach of the nucleophile to the carbon bearing the leaving group. Where is the nucleophile coming and attacking? Nucleophile is coming and attacking the carbon which is having the leaving group. The presence of bulky substituents on or near the carbon atom can have a inhibiting effect. See, I have already 3 or 4 people close to me. So if the fifth person is going to come to me, he will not have enough place to come and sit next to me, because I am already occupied by many people. So what happens? The effect of approaching by that friend to me will be less. But if I have only 2 people next to me, the third person can come easily and attack me, or can come close to me and sit. So this is called as effect of bulky substituents, which means simple alkyl halides, that is the primary halides will have more reaction towards SN2, that is SN2 reactions are favorable with primary alkyl halides, and tertiary alkyl halides will be the least reactive with the SN2 reactions. So this is the order of stability. If you see, primary will be more towards SN2, then comes secondary, then comes tertiary. If you see here, since this is tertiary, the nucleophile has no place to come and attack, already bulky groups are present. So this attack of the nucleophile to this carbon center is actually hindered. If you see the secondary also, similarly the attack is getting hindered. Primary, of course, not that when compared to secondary and tertiary, so the reaction actually takes place little bit smoothly. Next we will come to SN1 reaction. In SN1 reaction, when I said SN2, it is bimolecular, SN1 is actually unimolecular, where the rate of reaction depends on the concentration of only one of the reactant. That is, though there may be 2 reactants, the concentration of only one reactant is considered. SN1 reactions takes place in polar protic solvents like water, alcohol and acetic acid. The reaction between tertiary butyl bromide, tertiary alkyl halide plus an hydroxide ion. Now this is a 2-step process. How does this takes place? I have my tertiary group and I have my alkyl ion, which is my leaving group. This is my nucleophile. So how does this reaction take place? In the first step, the CBr bond undergoes a slow cleavage, a small break. So to produce a carbocation, what is a carbonium ion or a carbocation? Carbon, when it is valency is not getting satisfied, you know, it will occupy a positive charge, which is called as a carbonium ion or carbocation. So here it produces a carbocation and you get a bromide ion which is being left here. This is my leaving group. So this C with 3 methyl groups and a bromide, the CBr bond actually breaks. So you get a carbonium ion here with a bromide ion, which is the leaving group. So now this center is now ready to get attacked by a nucleophile. So the first step is the leaving group goes away. So what is my second step? Attack of my nucleophile. So the nucleophile comes and attacks my positive center, which is my carbon center. So it can attack from any side, right? So what happens? It comes and attacks on the same side. So you get here CH3COH. So there is a retention of configuration. You don't get the structure getting inverted. So but this is a 2-step process where the concentration of one of the reactant is considered. That's why you call it as SN1 reaction. So when I said in SN2, primary halides are more susceptible to SN2, tertiary or not. Here tertiary are more susceptible because tertiary carbonium ion are more stable when compared to secondary and primary. So primary halides undergo SN1 reaction with very least reactivity compared to secondary and tertiary. So in SN1, tertiaries are more stable and in SN2, primary are more stable. Now we will see that. Step 1 is the slowest and reversible, that is the slowest rate determining step. It involves the CBr bond breaking, for which the energy is obtained through solvation of halide ion. Halogen atom comes out with the proton of the protic solvent. Since the rate of reaction depends on the slowest step, the rate of reaction depends only on the concentration of tertiary alkyl halide and not on the concentration of the hydroxide ion. So what happens? Greater the stability of carbocation, greater will be the formation of the alkyl halide and faster will be the rate of reaction. So in this SN2 if you see, primary are more stable, and in SN1 if you see, tertiary are more stable. Okay, so this is one of the reason which they have given for allylic and benzylic. So children, you try to do the solutions that are given in the textbook to you without fail. Now we will get into the stereochemical aspects of the haloalkanes and haloarenes. Now we will get back into the stereochemical aspects of nucleophilic substitution reaction. What do you mean by stereochemical aspects? Stereo is nothing but space. Now how does this alkyl halides contribute the spatial arrangement, or how does that impact the structure of the alkyl halide is what we will be seeing now. Now to understand that, we need to learn certain principles like optical activity, chirality, retention, inversion and racemization. Let us learn one by one. Optical activity. Plane of polarized light produced by passing ordinary light through nickel prism is rotated when it is passed through solutions of certain compounds. When a plane polarized light, that is when a passing a light through the nickel prism through a certain compound, when it rotates the plane polarized light, such compounds are called as optically active compounds. Now that angle through which it is rotated, this is my compound, this will be rotated through the light. So that angle will be calculated using an instrument called polarimeter. Now there can be two type of rotation. One can be rotated the structure through the right side or rotating the structure through the left side. Now when the rotation takes place in the clockwise direction, you call it as dextrorotatory, or when it takes place through the left side, that is through the opposite side anti-clockwise, you call it as levorotatory. Dextrorotatory are being recognized using a positive sign before the degree of rotation. Similarly, levorotatory are mentioned using a negative sign before the degree of rotation. Now any sort of isomer, when it has both positive and negative, are called as optical isomers, and the phenomenon is called as optical isomerism. What are isomers? The compound is remaining the same, only their structures are different. So this is my compound. When it rotates through the clockwise, I call it as a positive isomer. When it rotates through the left side, I call it as a negative isomer. So I have dextrorotatory and levorotatory. So both are my optical isomer, and the whole process are called as optical isomerism. So this is with optical activity. Now let us see what is molecular asymmetry, chirality and enantiomers. Crystals of certain compounds exist in the form of mirror images, laid the foundation of modern stereochemistry. What is mirror image? I see myself in the mirror. When I raise my right hand, it becomes left. When I do something with my left, that becomes my right. So these are called as mirror images, where it cannot be superimposed. When I keep my right here, that becomes my left. So when I keep the right on the left, that does not go synchronized. So that we call it as non-superimposable images. Now the difference in the optical activity was associated with three-dimensional arrangement of atoms. Only with 3D atoms, the optical activity was studied. Now let us see how does this work. Spatial arrangement of 4 groups. There are 4 groups around the central atom is tetrahedral. Now carbon having 4 groups around it, it forms a tetrahedral shape. And if all the substituents attached to the carbon atoms are different, carbon's valency is 4. So when 4 different groups are attached to the carbon atom, it forms a tetrahedral structure. The mirror image of the molecule is not superimposed. You cannot overlap the one carbon structure with a mirror image of the same carbon structure on the molecule. Such a carbon is called as asymmetric carbon or stereocenter. You are able to follow me, children? When I keep my right hand over the mirror image of it, it is not superimposable. It does not get overlapped. So, such carbon which is having a tetrahedral structure with a valency of 4 with 4 different groups, which is non-superimposable on its mirror image or forms an unoverlapped image, you call it as a asymmetric carbon. Now, the asymmetry of the molecule along with non-superimposability of mirror image is responsible for the optical activity. Now, you have an example here, see. This becomes non-superimposable with my left leg and my hand, but here the same thing, when I keep it on its mirror image, it can get overlapped. Now, this ball I can get overlapped with the other one. So, these are symmetry, they are not asymmetric. So, those are called as chiral objects, or the carbon which is having 4 different groups which cannot be non-superimposable, you call it as a chiral compound or chiral carbon. The other one is a chiral carbon. See this example, children. This is my A compound, propane 2-all, carbon here, methyl, methyl, hydrogen and OH. If the mirror image is like this, again the mirror image will be the A and C remains the same. So, this is one rotation, this is one more rotation. So, A and C will be the same rotated images. Okay. Again, see, D is its mirror image of butane 2-all, CH3, C2H5H, this has come on the opposite side, but when I rotate, what happens? Only these groups actually go differently. So, none of them are superimposable. So, butane 2-all is a perfect example where it is a chiral carbon, or I can show it, this shows optical isomerism very effectively. Now, chirality we have learnt with carbon having 4 different groups which are forming non-superimposable images. Now, the stereoisomers related to each other as non-superimposable mirror images are called as enantiomers. So, instead of calling them as optical isomers, you call them as enantiomers. Enantiomers possess identical physical properties like melting point, boiling point and refractive index. What do they differ? They only differ with respect to the plane of rotation. If one is dextro-rotatory, the other one will be levo-rotatory. That is, one enantiomer will be rotating towards the right, the other one will be rotating towards the left of rotation. A mixture which contains 2 enantiomers in same proportion. If both the proportion of the enantiomers are same, it will have 0 optical rotation, which means the rotation of one will be cancelled by the rotation of the other, because they become superimposable then. So, right, such mixture we call it as racemic mixture, or we call it as racemic modification. Very important, understand. Enantiomers are 2 different isomers having different plane of rotation, but when they are equal in proportion, they become a racemic mixture because their rotation get cancelled with each other. The process of conversion of enantiomer into a racemic mixture is called as racemization. So, what it is called as? Racemization. Okay. Now, we have learned what is enantiomer, optical activity, chirality. Now, this is something which is retention. We learnt about SN1 and SN2. In SN2, we saw the product was inverted configuration, but here in SN1 we know it is retention in configuration. Retention in configuration is the preservation of the spatial arrangement of bonds to an asymmetric center during a chemical reaction. That is, whatever is my reactant, the product is also the same. The structure remains the same, only my groups may be different. That is, no bond to the stereo center is broken. The bond does not get broken or does not go away. The product will have the same general configuration of the groups around the stereo center as that of the reactant. If you see this example, what is happening here? There is a breakage here, but the structure remains the same. There is no change in the stereo center, it remains the same. Only OH will be my leaving group, the chloride ion comes and attacks here. So that is the only difference that is happening here. Such compounds or such centers we call it as a retention configuration. Okay. Inversion, retention and racemization. Again, with one example we are going to learn order 3. This is my compound. Now closely observe this. I have my carbon center, 4 different groups attached. One is X, a halogen. I have my hydrogen, one ethyl group and one methyl group. Now when Y is going to attack this compound, let's say we form the product B, but where this Y is formed on the other side. So there is an inversion in the configuration of this structure. But again, when Y is attacking, let us assume Y attacks at the same position, so you get a retention of configuration. So retention, inversion together A plus B will become racemization. So that is what is the whole process is all about. Now when you take retention, inversion or racemization with SN1 and SN2 reaction, in case of optically active alkyl halides, the product formed in SN2 is inverted in configuration. Why it became inverted? Because there is no space for the nucleophile to attack at the front side. Only from the back side the attack takes place. So that's why this becomes SN2, is becoming an inversion in configuration. That's what we learned here. The OH comes and attack at the back side of the substrate, not reactant, not at the front side. But what is happening in SN1? Any side it can attack. Now assume that if it attacks at the front side, you get a retention in configuration. If it attacks at the back side, you get an inversion in the configuration. So this can be even a racemized product. So SN1 you cannot say it is always a retention in configuration. It depends on the attack, the position of the attack from the front side or the back side. Okay. So that is till now we have learnt about stereochemistry, that is optically active compounds, enantiomers, chirality. We learnt about racemic mixtures, also about racemization with SN1 and SN2. Now some of the reactions where haloalkanes undergo are elimination reactions. Elimination reactions means something is getting removed. I eliminate it, I discard it. When a haloalkane with beta hydrogen, what do you mean by beta hydrogen? See, I have here, should understand, carbon which is holding my halogen is actually my alpha carbon. The carbon which is holding my halogen is the alpha carbon, or I would also say as primary carbon. Now this carbon which is holding the halogen, there is an adjacent carbon to that we call it as a beta carbon. So that beta carbon will be what? Will be the second carbon, secondary carbon. So here haloalkane with the beta hydrogen is heated with alcoholic potassium hydroxide with KOH. There is an elimination of hydrogen from the beta carbon and halogen from the alpha carbon. So this halogen along with the hydrogen is getting removed. Dehydrohalogenation takes place. As a result of the alkene is formed as a product. Since beta hydrogen is removed, you call it as a beta elimination. Let's see now what is exactly beta elimination. We learnt about Markovnikov rule, right children? Similarly, there is one more rule which we call it as Zaitsev rule. This is pronounced as Zaitsev. According to this rule, in dehydrohalogenation, what is dehydrohalogenation? A hydrogen and a halogen is being removed. It is removed. Preferred product is that alkene which has greater number of alkyl groups attached to the doubly bonded carbon atoms. So, this is my reactant. I have CH3, CHBr, CH2, CH2, CH3, that is 1, 2, 3, 4, 5, 2-bromopentane. Now, when a nucleophile is coming and attacking, there can be two products formed. I can lose my hydrogen from here, bromine from here, so double bond is at the first carbon, or I can take this hydrogen and this bromine, so I have a double bond formed at the second carbon atom. Now, why this is preferred when compared to this? Because according to Zaitsev rule, the hydrogen from the beta carbon, this is my alpha carbon, this is holding my bromine. So, I have two beta carbons, this is my beta, this is also my beta. So, there are two beta carbons which are attached. So, this bromine can take this hydrogen or it can also take this hydrogen. Now, according to Zaitsev rule, the hydrogen will be removed from the carbon which is having more number of alkyl groups. So, double bond will be formed between the carbons that is holding more alkyl groups. If in this side I see only one alkyl group is present, but here there are more alkyl groups present, this is bulkier. So, what happens? The bond will be formed here. So, hydrogen will be lost or removed from this carbon atom. This reaction we call it as beta elimination, and the process it follows is Zaitsev rule. Next one is reaction with metals, where we are going to see how haloalkanes react with metals. They also react with metals to form Grignard reagent, the most important thing which you will be using this throughout organic chemistry. Most organic chlorides, bromides, iodides react with certain metals. They react with metals containing carbon metal bonds. Such compounds are called as organometallic compounds. Organometallic compounds. These are my Grignard reagent. This is my R, CH2, CH3, ethyl alkyl groups is R, MgX is called as Grignard reagent. These reagents are prepared by the reaction of haloalkanes with metal magnesium in presence of dry ether as a solvent. Excuse me children. So, here I have my bromoethane, ethyl bromide with magnesium. In presence of dry ether, it forms my Grignard reagent. Now, let us see what happens here. Grignard reagent, this carbon magnesium bond is actually covalent because the electron negativity difference is actually very huge. So, carbon start pulling the electrons towards itself from the magnesium. So, the bond actually this becomes ionic and this becomes covalent. RMg is covalent, MgX becomes ionic. Right. Grignard reagents are very highly reactive, so they react with water to form RH, that is hydrocarbons also. The next one is most important, which is Wood's reaction. Very important name reaction which will be asked often in the exam. Alkyl halides, when it reacts with sodium in dry ether, they haven't mentioned here, but in presence of dry ether, what happens is that this halogen will attack my sodium. So, I get here sodium halide, and with RR, that is a hydrocarbon is formed. So, Wood's reaction is for the preparation of hydrocarbons. So, with this the reactions, that is the main reactions are over with haloalkanes. Now, we will be studying about reactions of haloarenes. So, now we shall learn about reaction of haloarenes. Aryl halides are extremely less reactive towards the nucleophilic substitution reactions. So, compared to our alkyl halides, aryl halides are less susceptible, means they do not undergo nucleophilic substitution reactions, or I would say they do not undergo substitution reactions as easier compared to that of alkyl halides. Now, what could be the reasons why such reactions do not take place? First effect, there are these reasons are very important children, often asked in your board exam. So, please make sure that you mark it in your textbook when you are listening in the class. Resonance effect. In haloarenes, the electron pairs on the halogen atom are in conjugation with pi electrons of the ring, and the following resonating structures are possible. If you remember, last year we were writing the resonance structure, how the electrons get shifted in each of the positions. Now listen this structure carefully. I have a benzene ring. This is my halogen atom. 1, 2, 3, 4, 5, 6, 7, 8th electron is forming a bond here. Now what is happening? These electrons comes and joins with the bond here. So it forms a double bond. The bond which is inside in this carbon-carbon comes out, takes the ortho position. So this becomes my electron rich center. So definitely I should put a negative sign. Now what is the next structure? These electron forms a double bond inside, and the adjacent double bond sends the pair of electrons at the para position. So there comes a negative charge here. Now what is the next structure again? These electron forms a bond here. So I get a double bond, and the bond adjacent bond sends a pair of electrons at this center. So it bears a negative charge. This is how this goes again and again. Why? So what is the reason for not having a nucleophilic substitution reaction? We know nucleophiles will attack only the electrophilic center, where there is a carbon having an electron deficient center. But here almost all are electron rich. So the carbon chlorine bond acquires a partial double bond character due to resonance. So the bond cleavage in haloarene is difficult. What do you mean by bond cleavage? The breakage of the bond becomes so difficult because of the carbon halogen double bond character. Therefore, they are less reactive towards the nucleophilic substitution reaction. Now if you see the next two reasons, difference in hybridization of the carbon atom in haloalkanes and haloarenes. If you see haloalkanes, it is sp3 hybridized. That is, in case of haloarene, it is sp2. So what difference does it make? The sp2 hybridized carbon with greater s character, sp2, right? Here it is sp3. So the s character is actually much less when compared to that of sp2. Is more electronegative and can hold the electron pair of CX bond more tightly than the sp3 carbon in haloalkane. Just for the reason that the S strength, the character of S orbital is more in case of sp2. So it can hold the pair of electron towards itself. So the breakage of the bond becomes difficult. So in such cases, the CCl bond length in haloalkane is 177, but in case of haloarene it is 169. Since it is difficult to break a shorter bond when compared to a lengthier one, haloarenes are less susceptible towards the nucleophilic reaction. So the first one was the resonance effect, second one was due to the type of hybridization of the carbon bond, then the third one is instability of the phenyl cation. C6H6 is benzene. When it loses a proton, it becomes a phenyl cation which is not stable as compared to that of my benzene. So because of that, it does not undergo nucleophilic substitution reaction. And the last reason is because of the possible repulsion. It is less likely for the electron rich nucleophile to approach electron rich arenes because already they are rich in electrons. So when a nucleophile comes and attacks, there is a repulsion, so there is no bond formation. Now let us, with these reasons, let us see how does arenes undergo reactions. So the first one we will see with replacement of hydroxyl group. Chlorobenzene, this is my haloarene. When it is treated with phenol in presence of a mineral acid or at 623 Kelvin, what happens? The alkyl, that is the halide ion, comes out as a leaving group and this OH comes and attacks. So actually you get NaCl as a byproduct and you get your phenol. So this is how haloarenes where undergoes reaction with a hydroxyl ion. The presence of an electron withdrawing group at ortho and para position increases the reactivity. Again, I want you to remember your +1 class where we have learned about electron withdrawing and electron releasing group. So this is my electron release withdrawing group NO2. Once it withdraws the electron, the reaction actually becomes more faster. See here, with 2NO2, again the reaction is actually faster. You can see the temperature actually once it was 623, with a withdrawing group it becomes 443, with 2 withdrawing groups it became 368. So when there are more withdrawing groups, what happens? The temperature actually comes down. Now we will see, with 3 withdrawing groups you just have to warm it little bit so that you get your phenol, trinitrophenol, 2,4,6 trinitrophenol. You don't have to learn this mechanism. Now let us see, still it does not undergo nucleophilic substitution. What happens when it undergoes electrophilic substitution? Because we know haloarenes undergo the electrophilic reactions of the benzene like halogenation, nitration, sulfonation and Friedel-Crafts reaction. Children, recollect your +1, we have learned this already. So this is my haloarene, again the same resonance structure taking place. Due to resonance, electron density actually increases at ortho and para position. So the electrophile, which is electron deficient, will come and attack my ortho and para position very easily than the meta position where there is no electron rich center. That is why we say electrophilic substitutions are more susceptible to the haloarenes. Now let us see some of the halogen nitration and sulfonation reactions of haloarenes. Now what is halogenation? The haloarenes, when it undergo with chlorine in presence of anhydrous ferric chloride, what is this? This is a catalyst. Role of a catalyst is to speed up the reaction. Not only speeding, this being a positive catalyst, it increases the rate of reaction. So you get the chlorine coming and attacking the para and the ortho position, because we know ortho and para positions are electron rich centers. So only those positions will be occupied by the halide ion. Now we will see what is nitration. In nitration, I can say chlorobenzene, when it treats with nitric acid as an oxidizing agent in presence of concentrated sulfuric acid. Always remember children, whenever you do nitration, definitely nitric acid with a combination of sulfuric acid is very important, because we think sulfuric acid has no role, but without concentrated sulfuric acid, nitration will not take place. So NO2 is being an electrophile, comes and attacks the ortho and the para position, and always para position becomes a major product. Next one is sulfonation. For sulfonation we use concentrated sulfuric acid and slowly heat it. You get SO3H, which is formed at the ortho and para position, 2-chlorobenzene sulfonic acid and 4-chlorobenzene sulfonic acid. So children, these reactions are very important in case of haloarenes. This also we have learned Friedel-Crafts reaction where you have alkylation and acylation. What is alkylation? Alkylation means alkyl part is being added. Acyl means COCH3 is called as acyl. This is acid chloride. So this acyl part is actually getting added. So we call it as an acylation. In Friedel-Crafts alkylation, same chlorobenzene with CH3Cl, you use anhydrous aluminum chloride in 3 reactions: halogenation, Friedel-Crafts alkylation, Friedel-Crafts acylation. So this is being used as a catalyst. So what do we get here? We get the alkyl part coming and attacking the ortho and the para position. So this is 1-chloro 2-methylbenzene or 4-chloro 1-chloro 4-methylbenzene. So this is again alkylation where the methyl part comes and gets attacked to my haloarene. In acylation what happens? This is RCOCl, that is CH3COCl. Cl part is being broken, COCH3 comes and attack my chlorobenzene. So I get here 2-chloroacetophenone, 4-chloroacetophenone. No, words are very new for you children, but definitely you have to learn it by heart. These reactions are very important. You get in name reactions, okay. So these are some of the reactions of haloarenes. Now the last one we have reaction with metals, two important reaction. You remember children, Wood's reaction we were learning to make aliphatic hydrocarbons. Here the same haloarenes will be used with a Grignard reagent. Again you remember, mixture of alkyl halide and sodium in presence of dry ether. So you get RMgX here. So what here happens here, instead of aliphatic hydrocarbon you get an aromatic hydrocarbon. So what happens here, R comes and attacks and you get NaX removed. So this reaction we call it as Woods-Fittig reaction. So in Woods-Fittig only one haloarene reacts with sodium and Rx in presence of dry ether. You get one molecule of aromatic hydrocarbon. But in Fittig reaction, aryl halides, two molecules will react with two molecules of sodium in presence of dry ether to form diphenyl. Two halogen atom combines with sodium to form NaX, and these two benzene rings will form a bridge over here which is called as diphenyl. So that is called as a Fittig reaction. So we learnt Wood's reaction, we learnt Fittig reaction, together Woods-Fittig reaction. So these are some of the reactions which we have learnt till now. So look at the solutions. Now we will get into some of the organometallic compounds, or we will say polyhalogen compounds, which will come in 1 mark question for you. Dichloromethane, trichloromethane, with all this where it is being used like as a propellant in aerosols, and also it is being used, methylene chloride harms the human central nervous system, highly poisonous. In humans, direct skin contact with methylene chloride causes intense burning. So these you just have to give a reading with some of the polyhalogen compounds. Chloroform, 1 mark question again. Chloroform, when it is burnt in oxygen in presence of light, you get phosgene, which is a highly poisonous gas. That is why it is stored in dark colored bottles which is completely filled so that air is kept out. Okay. And then triiodoform you learn, CCl4 carbon tetrachloride. Freons, again it is a 1 mark question children. The chlorofluorocarbon compounds of methane, ethane are together called as freons. 1 mark question it comes. The structure will be given to you, Freon 12, they will ask you to write the formula. The formula will be given, you have to write it. It is manufactured using Schwarz reaction. If you remember, we learned for preparation of fluorine compounds. Okay. So there it is being used. Then comes DDT, dichlorodiphenyl tetrachloroethane. So learn the structure, learn the use, how it is being used, how many chlorine atoms are present, and also learn the expansion. So these are all comes in only 1 mark questions for us. So with this the chapter gets over. I hope you are able to understand halogen compounds. The first lesson of organic chemistry, though it has lot of reactions, definitely you have to write the reactions more and more times so that you learn it by heart, because memorizing is very important in this. You cannot just change the reactant and the product of your own choice. So when it's a preparation is asked, you should write the concerned preparation, similarly the properties and also the name reactions. You cannot change the reactant. So don't feel it hard after your improvement exam is got over. Spend time for organic chemistry, because it is actually the most easiest part. If you learn it by heart, definitely you can score full marks in this, right? So more easy for getting more marks is organic part. So with this the chapter gets over. We will try to do HSS live questions also, simultaneously try to see the repeated questions in the board exam. So then take care children, have a great day, bye.